Hey, okay, great. All right. Well, I'm Robert Haas. I work at Enterprise DB. This is my talk on query planning gone wrong. I gave this talk at pgsql this year, so if you were there, then there's nothing new here. But you can still stay and listen again if you really thought the talk was that good. At Enterprise DB, I'm the chief architect for the database server, which means that I am responsible for coordinating a team that handles both our proprietary version of PostgreSQL, which is called Advanced Server, as well as our contributions to community PostgreSQL. And we're doing some pretty cool stuff for the 9.4 release, but that's not what I'm here to talk about today. Instead, I'm going to tell disaster stories. The origin of this talk has been a couple of years in the making. The first PostgreSQL conference talk I ever did was in 2010. And I gave this talk about, probably 8 times. It was called the PostgreSQL Query Planner. I guess I've only really ever had one good PostgreSQL talk idea, and I used it up the first time through. So, but that talk, people kept asking me to give it, and I kept giving it. And what I talked about in that talk is how does the query planner actually work from a user perspective? What does it really do? What kinds of things is it deciding between? What is it trying to accomplish? People like the talk, but they often asked, well, okay, it's nice to hear about what it's supposed to do, but what do I do when it breaks horribly? What do I do when it fails? How do I fix my query? And I didn't really have a good answer to that question. I've been using Postgres long enough that I've fixed a lot of queries that weren't working properly, but I didn't really have anything systematic to explain, well, what's the general pattern here? What are the most common things that break? I had no idea. I just knew how to fix individual things. In 2011, Tom Lane gave a talk on hacking the query planner, which sort of tackled the same question from a developer perspective. In other words, my talk was about, well, what do you as a user see when you look at the output of the query planner via explain, for example? And what Tom talked about is how does it actually do that stuff under the hood? What's really going on internally? And he included a plea in that talk for help improving the query planner. But again, it leads to kind of the same question. So if we want to improve the query planner, well, what should we be improving? What works less than perfectly now? And I felt like I didn't have a good sense of what those things were. I didn't have any data. And so I tried to gather some. So here's what I did. I read hundreds and hundreds of email threads on PostgreSQL-performance over a period of almost 2 years. And I threw away all the ones that were not about query performance problems. So if it was about system performance or hardware selection or any topic other than, why is my query slow, I just disregarded that for purposes of this data gathering experiment. And then I decided in my sole and infinite discretion what I thought the cause of that query being slow was. I skipped a couple, a very small number where I couldn't form an opinion. And then I just counted up the number of times each problem was reported. And that's the data I'm going to talk through with you today. Now, you might be saying to yourself, in fact, I hope you are saying to yourself, that is a terrible methodology, because you're right. The problems that are reported on the PostgreSQL performance mailing list are not necessarily representative of all the problems that PostgreSQL users encounter. In fact, they almost certainly aren't. Problems that people solve easily in 5 minutes are unlikely to be reported. And there's also a bias in terms of which users are likely to post to the mailing list. Novices might not even know that the mailing list exists. Experts might already know the answers. Big companies might have support contracts and might go through their provider rather than through the mailing list. So there's lots of reasons why this is far from completely accurate. And a second problem is me. I might have failed to correctly identify the cause of each problem. It's difficult to be 100% objective here. I did try, but the data won't be any better than I am, and you can form your own opinions about how good or bad you think that is. For all of that, for all of those drawbacks, I found the data that I gathered to be pretty interesting, and maybe you will as well. So statistically speaking, why is my query slow? So N for this talk is 168. I ended up with 168 reports after pouring through all of these performance emails. And I sort of started out by classifying each one, at a very detailed level in a sentence or so what the problem was. And then I realized that just gave me this huge mess that nobody could make any sense of. So I started to try to group them into buckets. And so this is what I came up with. There were 23 cases where I felt that the problems were attributable to settings. There was something that the user needed to change to create the optimal environment for their query to have the best chance of running fast. So maybe they needed to modify PostgreSQL.conf, or they needed to make some DDL changes, or maybe they even needed to change an operating system level setting. And then I had 23 cases where I said that the problem is that that's just plain slow. You're asking for something to be fast, which fundamentally can't really be fast. So the problem isn't Postgres or your machine or anything else. The problem's you. The problem is you don't realize how much work you just asked the system to do. I'll go into each of these in a little bit more detail. But these are often questions of the form, why is A slower than B, when in fact A is actually doing something that's intrinsically much more expensive and should be much more expensive than B. But the user just doesn't see that. Then I had sort of a catch-all category, which I'm calling we're bad at that. So in this category, I put the things that could be fast, hypothetically, in some other database system. But in Postgres, they are not fast, either because we haven't implemented those things yet or because we've made certain architectural choices which may have advantages in other areas, but for these queries in this situation, they stunk. And then the biggest category by far, accounting for half of the total here, was planner error, by which I meant bad decisions about the cost of one plan versus another plan due to limitations of the optimizer. So these are all the cases that we could have gotten right if we were smart enough without any fundamental rewrite of the system. And that's a lot. That's a lot of planner errors. There were 14 cases that I attributed to bugs, mostly bugs in the query planner, but one of them was a Linux kernel bug. Then there were a couple of reports where basically the user was just really confused about what was going on. And maybe they wrote a query that didn't actually produce the result set that they were asking for or something like that. Yeah. OK. So I'm going to go through these in more detail. But any questions before I move on? OK. So settings. People who have done a reasonable amount of query tuning on Postgres probably won't be terribly surprised to see that adjusting the planner cost constants was the single most popular problem in this area. If you don't get sequential page cost and random page cost right, correctly modeling the costs of sequential and random I/O on your system, it's likely that you're going to have some problems. I have always personally advocated modifying just sequential page cost and random page cost and leaving the other settings alone. My colleague Kevin Grittner advocates also modifying CPU tuple cost, and I wasn't able to determine from these 8 reports anything meaningful about which of those strategies is actually better in general. Which one the user actually tried was often determined by who got to the thread first and suggested a resolution, and then whatever hacker said, well, try this, the user would write back and report, oh, that worked great. And you couldn't really tell whether the other one would have worked better or worse. So I don't have any sound basis for telling you to prefer adjusting or not adjusting CPU tuple cost, although it'd be interesting to hear afterwards if anyone has any experience with that in their own environments. There were 4 reports that were resolved by adding an index. There were 2 reports that were attributable to the cost for the @sign text search operator being too low. That operator is actually more expensive than we have it listed as being in the system catalogs, and so sometimes that will push the planner into choosing the wrong query plan. There are a couple of cases where workmem was too low, and workmem, as some of you probably know, is the variable that controls how much memory the planner is willing to use for an individual sort, hash, or materialize operation. And if more memory would be needed than that, then we have to somehow go to disk. If you've tried setting workmem really high, you know that what happens is everything works great and is really fast until you have a load spike, and then you blow out system memory, everything starts swapping, and your system goes completely down. So there are no reports of workmem being too high causing a query performance problem on the list, and that's because it doesn't cause a query performance problem. It causes your system to go down. So, you know, that's something you've got to be aware of when looking at this data. But obviously, setting it too low can cause you problems as well, and you can sometimes see enormous speed-ups for raising that. You just have to be careful about how far you raise it and whether you do it for all queries or just the specific ones that are having problems. There's also something called the statistics target, which can be configured system-wide or on a per-table basis. There were 2 reports from it being too low, where the query planner didn't have enough information about the actual distribution to figure out the best possible query plan. And when you raise the statistics target, at least for the relevant tables, then it did get the right plan. There was one report where we had the opposite problem. The statistics target was too high. And as a result of the statistics target being too high, the planning time was very long. And so the user said, my query is slow. Why is your query slow? Because we're taking forever to plan it with this huge amount of statistics that you've asked us to gather. Yeah. I think it was set to 10,000. That might be too high. The planning time actually goes as n squared, and the default is 100. So, all right, so in the just plain slow category, there were a whole bunch of things here, but there were a couple of standouts. You know, the sort of number one idea is, you know, it takes a while to process a lot of data. You know, if you have a very big table and you try to add up all the values in a column or do something else that requires reading through all of that data and processing it somehow, your query is going to be slow. And you know, this seems kind of dumb when you see it listed on a slide here, but one of the things about SQL is that it's a declarative language. You can ask for any report that you want, any piece of data that you want, and the system will merrily go off and try to get it for you, and it won't tell you, hey, I don't have an index for that, so I can't do it. It'll say, he asked for this data, I'm going to get him this data no matter what it takes. And it does. So it's easy to ask for things that can't be computed efficiently. But of course, that can also be a positive thing, and that you can ask for whatever you want. And if you're willing to wait long enough, you'll eventually get it. The other big thing in this category was, you know, disks are slower than memory. Again, SQL conceals from you whether you're reading data from disk or reading data from memory. But if you've got 2 queries, and one of them by its nature forces disk reads and the other one does not, you know, it's a good bet the one that has to do disk reads is going to be slower than the other one. Most of these other things were reported just once each. The only other one that was reported more than once is clauses involving multiple tables can't be pushed down. So if you have something in your where clause, some expression, you know, a plus b, a dot b minus c dot d is less than q dot r, well, you're going to have to join all of those tables before you can evaluate whether that condition is true or false. And that's going to be slower than if you have things like a dot b equals 1, which can be pushed down and evaluated before you do the join. All right, we're bad at that. This is somewhat of a catch-all category. The thing that came up a lot here is there's a couple of plan types that we can't or historically couldn't generate in PostgreSQL that were very efficient for certain kinds of queries, but we just did not have the architecture to create those plans. Parameterized paths is the big one. that was actually added in 9.2. Out of these 7 reports, 2 were actually post 9.2 complaints, where it turns out that parameterizing the paths in the way that we can now do in 9.2 was not good enough, and you had to be able to parameterize even more complicated paths. But some progress has been made there. These are basically a nested loop where you have a value from the outer side powering an index scan or something more complicated on the inner side. So you look at each row in one table and you pull out a value and you use that to drive an index scan in another table. That very simple case where what you're doing is precisely driving an index scan on another table has been supported forever. But doing anything more complicated with that value from the outer table, like doing 2 index scans and then joining the results of those to each other before you do anything else, was not supported before 9.2. And you can construct queries with left joints and stuff where this makes an enormous difference in terms of performance. Merge append was added in 9.1. This came up for people who were still running older releases where they had queries on inherited tables that used order by, and they were just obscenely slow. And there's a bunch of other things here, mostly onesie-twosie kinds of things. I find the ones down here in the architecture category to be kind of the most interesting. These are things that we kind of all know if we've been around Postgres for a while, that these are kind of baked into our DNA. Table bloat, because of the way we do MVCC, it solves locking problems, but it creates these other issues. No parallel query, I'm working on that, but there's a lot more work to be done there before we actually get that. All of these are things which could be fixed given enough work, but they're really, really hard problems. And they're fairly deeply ingrained in what we do. But it's an interesting list to look over. All right, so here's the big one. Planner errors. The planner, you might think, errors a lot. But remember, this is only the things that people actually complained about. Certainly, there are lots and lots of queries where the planner does just fine. Sometimes in situations in which it's pretty amazing that the planner just does just fine. I had a 30-table join in production once and ran it like fast enough to run it inside of a web portal, and there's probably millions, if not billions, of different join paths there, and it was good enough. But in terms of the things people actually complain about, there are a lot of planner errors. This is a big category. So if you haven't previously seen these slides, take a guess at what the big items in this category are. Anybody want to take a guess who doesn't already know what the next 3 slides say? Greg? Correlated columns and index selectivity. Yep, that's one of the big ones. Oh, time ranges at the end of the index? No, not that one. Anybody else have a guess? Quiet group. At PGCon, everyone wanted to guess. All right, so here we go. I tried to break these down a little bit. I divided these into a couple of subcategories. The first category was conceptual errors. Okay, so what I mean by this is the planner doesn't recognize that 2 different queries are in fact equivalent. So it doesn't even consider the best plan. So these are, you can write the SQL this way and the planner will consider this set of plans, or you can write an SQL that's guaranteed to mean the same thing in some other way, and the planner will generate a different set of plans. Okay, that accounted for 28 of these cases. These are also known as the good cases, because in those cases, you can fix the problem pretty easily by writing the query in the different way that does cause the good plan to be considered. And then the other 55 were estimation errors, where the planner considers the optimal plan, but it rejects it because it thinks it's too expensive. And those kind of broke down into 2 subcategories. Row count estimation errors, where the planner misestimates the number of rows that will be returned by some scan, join, or aggregate. Or cost estimation errors, where the planner gets the row count right, but it incorrectly estimates the relative cost of the plan based on the row count. And at least in my opinion, or at least in my experience, I guess I should say, this data reinforces something which I kind of knew intuitively, which is when you have a query that isn't performing well, pretty much the first thing you want to do is check whether the row counts are being estimated correctly. Because if they're not, you're probably screwed. And that's a very, very common situation for badly performing queries. This group, it's got a bunch of things inside of it, but this group of problems, row count estimation errors, is easily the biggest cause of bad query performance, at least in this sample. And in my experience, that bears out pretty well on my own systems that I've had to troubleshoot as well, and on customer complaints and all sorts of things. All right. Questions on this? Man, quiet group. OK, so breaking this down, here are the grand prize winners at the detail level. The first one is what Greg said. Selectivity of filter conditions involving correlated columns is estimated inaccurately. 13 reports. To explain what this means, if we have a table and we want to find all the rows where A equals 1 and B equals 1 and C equals 1 and D equals 1 and E equals 1, the planner needs to estimate the total number of rows that will match all of those conditions. But it doesn't have any direct way of getting at that information. It knows individually what percentage of the rows have A equals 1, and what percentage of the rows have B equals 1, and what percentage of the rows have C equals 1. That is there in the optimizer statistics and is actually estimated quite accurately. But these columns may be positively or negatively correlated, right? So if you have some rows where A equals 1 and some rows where B equals 1, they may overlap completely or not at all. So if you just know 20% have A equals 1 and 20% have B equals 1, do you have the full overlap case, or the partial overlap case, or the no overlap case? The query planner has no idea. It has to guess. It assumes they're not correlated, which is a middle-of-the-road assumption since the correlation could be positive or negative. But you can have orders of magnitude of estimation error here, and that will screw up your query plans. Now, the other really big one was the planner incorrectly thinks that a query of the form select star from foo, where A equals 1, order by B, limit n, will fill the limit after rating a small percentage of the index. I see nodding in the audience from more than one person. And I bet we've all seen practically this exact query more than once if we've done any substantial amount of query troubleshooting. This query is my arch nemesis. I mean, like this thing up here, this top one, tends to show up in all sorts of very complicated queries, which may do the multi-column thing buried down inside some complicated other bunch of rigmarole. And so the problem is concealed to some degree. And eventually you dig it out and you're like, oh, it's another one of these. But this one, this second one here is, I mean, people actually write that exact query a lot. It's like, I want the top 10 web pages with the most hits, that are in category XYZ. Or I want the top 10 users with the most points, or whatever. Right? People actually write that exact query with foo, A, B, and N changed to various different values a lot. And it sucks. Sometimes it sucks. So the thing to realize about this query is that there are two pretty sensible strategies for evaluating this query. The first thing you could do is you could look for an index on B, which is the ordering index. And you could scan through it looking for rows where A equals 1. And then when you find enough to fill the limit, you could stop. Right? That make sense? OK. The second thing you could do is you could scan an index on A and find all the rows where A equals 1. And then you could perform a top n sort to find the ones with the highest B values. That would also be a sensible strategy for handling this. The query planner in this case tends to only err in one direction. It likes to do the first one in a lot of situations in which the second one would actually be better. I'm sure somebody's had the opposite problem at some time in the history of the world, but it's not me. And as far as I can tell, it's not anyone on PostgreSQL-performance in the last 5 years either. This can often be worked around with a composite or functional index. If you can often create an index on, say, both A and B, or on B with a where clause constraining A to be 1, and that new index that you create will look just a little bit better than either of the existing indexes and will actually be only slightly faster than the already good index, but you'll pick it and therefore come out ahead. But this can be a very, very frustrating problem, and it happens a lot.
So how does that optimize the decide which strategy to choose?
So,
does it rely on the selectivity of an index by A?
Yeah, so yes. So the question is, how does the planner choose between these two plans? It's just based on a costing model, right? But the thing where it falls down, it's actually very similar to the first problem. The thing where it falls down is that it assumes if it scans the index on B, the rows where A equals 1 are going to be uniformly distributed. So if half of the rows have A equals 1 and you need 10 rows, you assume that if you scan 20 rows from the index, about 10 of those will have A equals 1 and you'll be all set. But sometimes it turns out, funny thing here, that the columns are correlated and then all the matches where A equals 1 are at the end. So you scan through 1 million rows where A is not equal to 1, and then you have another million rows where A is equal to 1, and that's 50%. But you have to scan through 1,010,000 rows instead of 20 to find the number of rows that you need, and you just want to kill yourself.
So the selectivity by A is not taken into account ever?
No, the selectivity by A is taken into account because it uses that to estimate how far it will have to scan through the index on B.
Okay.
So if A equals 1 is very rare, you're probably not going to have a problem with this query. If there are very few rows where A equals 1, then it's going to say, geez, if I scan the index by B, I'm going to have to scan a long way through that index before I fill the limit, and this is going to be slow. And it's right. But the problem is that sometimes, even when there are lots of rows where A equals 1, none of them are near the index. And so you end up having to scan and scan and scan and scan and scan. And sometimes you can have both of these problems in combination, where actually there are no rows at all that meet the criteria. And you scan through the entire index trying to find one row that matches the criteria. And the planner is like, oh, yeah, we're going to find that in like no time. And in fact, you never find it. And you scan through the entire index looking for it. Yeah, it's an ugly problem. All right. This is like therapy. Everybody who's confronted this problem is like, oh my God, I'm so glad to see that on somebody's slide. All right. Whoa. All right. So other row count estimation errors. Using with can result in a bad plan. There are actually two different issues that are conflated under that category. With queries don't get what's called flattened into their parent query. So we kind of plan the with query separately from the main query. And so people sometimes think that they can use with to make their queries more beautiful. And it does, but it also makes them slow because we can't make as good a planning little pieces of the query individually as we can planning the entire query as a unit. I am of the opinion that the way that we handle this is actually a bug, but not everybody agrees with me. Because some people think that the behavior here is actually useful to people who want to control how their queries are planned. And then the other problem that's lumped in here is a failure to dig out variable statistics. If the with query refers to variables that are to columns that are set out to column values that come from outside that with, we actually won't go and look up the selectivity of those variables. We just use a set of default assumptions. And things things can come unscrewed. So I think the takeaway here is use with when you really need to, not when you just feel like using with. Try to avoid it unless you've got a really good reason for thinking that it's going to be better, because our optimization in this area is just not that exciting. This feature went in 8.4, and I was kind of hoping eventually we would make some progress on optimizing this, but nobody's put in the effort yet, unfortunately. So it's still pretty primitive. Now, another problem in this general category is generic plans can have wildly wrong estimates. So this is like the case where you have a query like, select star from foo where a equals 1. If a equals 1 is a very common value, you probably just want to sequential scan the table, because nothing else is going to be faster. But if a equals 1 is an uncommon value, then you want to use an index. Well, if you use prepared statements, either the SQL prepare command or like a JDBC type connector, which prepares everything at the protocol level, then what the query planner actually sees is select star from foo where a equals and we decide on the plan without knowing what actually is. The good news is that allows us to reuse the plan if you execute the same prepared statement multiple times with different bind values. But the bad news is that if all of those different bind values don't need the same plan, then sometimes you're going to get the wrong plan. This has been improved, and I use the air quotes intentionally, in 9.2. And we now try replanning a few times to see whether we're getting different plans for different bind values. And if we keep getting the same plan, then we just always use that plan. And if we don't, then we keep replanning every time. I think this has probably helped some people. It's also hurt some people, because it turns out that as annoying as it was to not replan the query ever, replanning actually has a cost to it. And sometimes people who were happy with the old system are now unhappy with the new system because they're getting that replanning behavior, hurting the performance of their queries, and maybe they're not actually any better off than they were before. Another thing that sort of comes up here is, selectivity estimates on arbitrary expressions are poor. So what this means is, if you put in where something, right? If you put in where a equals 3, that's one of the limited number of things that the query planner understands exactly what that means, and it will estimate it well. But if you put something like where a plus b is less than 10, the query planner has no idea, right? It doesn't try executing that with a bunch of sample values from your data to see what happens. It doesn't do anything nearly that sophisticated. It just says, I don't know what that is. And it uses some kind of generic estimate, which may be accurate, and it may be wildly, wildly inaccurate. My classic example of this is a plus 0 equals a. The actual selectivity of that is 1 minus null frac, because that will be false for any null rows in the table. But for any non-null value, a plus 0 equals a is going to be true. So the correct selectivity estimate for that expression is 1 minus null frac. The actual selectivity that you get with the query optimizer is 0.5%. Done, 0.5%. So sometimes that doesn't work out.
But we always use this to suppress the usage of indices. That was like the ages-old trick. Do not fix it.
Yeah, so she's saying you can use this trick to, you can deliberately do this on purpose to fix broken queries. I've actually done that once, but I don't like to admit it. Yeah, there's some really ugly things you can do to get around some of these things. And then this next one here is joint selectivity doesn't know about cross-table correlations. This is the direct analog of the number one big one on here, except it's an even harder problem because this is the case where you have that problem, but the correlation is across two different tables. So rather than having data that's correlated between two columns in the same table, you have data that's correlated between two columns in completely different tables. Ugh. And there's a bunch of smaller things here. I don't think it's probably a good idea to take the time to go through each one of those individually, but if there is any particular one up there that somebody wants to ask about, I could go through those.
Can you talk about redundant equality constraints? Because that's another thing which, like, I personally used for the longest time to improve queries. Can you talk a little bit about it?
Yeah, so sometimes you can have a query. I'm not sure if it happens if you get a problem in a case that's as simple as a equals 1 and a equals 1 and a equals 1 and a equals 1, or if you have to be a little bit more clever than that to trick the query planner. But where this comes up, right, is people have these systems, these query generation systems, that take in input from the user and they generate a query in SQL to send to the backend database. And they're not always that smart, right? They submit queries that to a human user you can easily see, well, you've got redundant stuff in here. So an example that is a little bit non-trivial might be something like you have a two tables foo and bar that you're joining, and foo.x equals, or like, let's see, foo.x equals bar.x. No, that won't quite do it. I'm not sure exactly how clever you have to be here in order to.
When you join and you put constraints on the join criteria from both sides.
Yeah, but if there are equality constraints on both sides of the joint, it actually it actually will recognize that. If there are inequality constraints, it won't. Like if you say a.x equals b.x, and a.x is less than 1, and b.x is less than 1, it won't recognize that those are redundant. That would actually be different from this, though, because this was a complaint about redundant equality constraints not being identified, and that would be redundant inequality constraints not being identified. So I don't remember exactly what the situation with that one is.
We'll check it out.
Yeah, I have on my website, if you Google like Robert Haas presentations, I've actually got all of this data on my Google site, and you can click back through to the original report that prompted that line item and see what was going on there and form your own opinion about whether, what was going on there and whether I'm right about any of this. Enlist? Yeah, so we were incorrectly estimating the selectivity of something like a.x in open parentheses 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, close parentheses. That's actually been fixed. Okay, cost estimation errors. There weren't a lot of these, but there was a clear winner. The planner does not know that detoasting is expensive. This actually is sort of the same issue, or is closely related to this issue about the cost for the at operator being too low. They may actually be both complaining about the same thing in different ways. But the problem here is that some nodes in the plan tree require that you actually detoast the tuple. So toasting is our method for storing large values out of line. So if you have anything that's larger than a couple K, it's actually going to get invisibly pushed into a side table. And you never really have to know that's happening because, from a correctness point of view, because that data gets sucked back in and incorporated into the tuple automatically behind the scenes. However, from a performance point of view, the effects can be very visible. You start to make your data values larger and larger, and eventually the tuple becomes big enough that parts of it start getting toasted, and your performance tanks because now you have this secondary table that you've got to go and access. And when you're working through the process of evaluating a query, some of the nodes in the query planner will detoast the entire tuple or detoast specific fields, but the places where those operations happen don't affect the cost calculation that the query planner makes. So you may have one plan that's faster than another plan, even though it looks like it should be slower, because the faster plan picks a better place to detoast than the slower plan. And like I say, right now the query planner isn't smart about this at all. It just sort of detoasts where it feels like it needs to detoast. And it doesn't, there's no logic to decide whether it should happen here or there. It just kind of happens somewhere at the first place that there is, that information is needed. And that turns out not to be so good. One of these cases was a case where somebody inserted a window ag into a query that didn't actually do anything. It was like just some like dummy column that did no computation. But the window ag node that they put in there forced every tuple that went through that node at the plan tree to be detoasted. And their query got faster because somewhere up above that there was a nest loop join. And having things already detoasted when it reached the nest loop caused the detoasting to only happen once. Whereas if you waited until you were above the nest loop to detoast, you ended up detoasting the same data multiple times. And that wasn't good. This can cut both ways. But clearly, this is a small category, but that particular thing is definitely a recurring theme that I think we're probably going to need to fix at some point after we get around to fixing all the other really hard problems. Questions on this? Yeah, I guess the other thing here that happened twice was that there were two plans. One of the plans seemed like it would be faster, so the server switched. But it turned out that the faster plan actually accessed more data, and it blew out the server memory. And so instead of having no I/O, you had a whole bunch of I/O, and that wasn't good. The planner does not attempt to estimate whether the amount of data that it's touching is going to result in disk I/O. All right, conceptual errors in the planner. So these are cases where the query planner just can't really recognize that things are equivalent. So one of these is like you have an integer column called a, and you have a equals 1.0 in your query. Well, if you ask Postgres, is 1 equal to 1.0, it'll be like, yeah, totally. Integer, floating point value, no problem comparing those. But it doesn't have the infrastructure to know all the values that it might have to find in the index that could potentially be equal to 1.0. Right? So if you say where a equals 1.0, and it's trying to do that with an index scan on an integer index, it would have to know, if the constant is 1.0, I can just look for 1, and that will be just as good. And if the constant is 3.5, I don't even have to look at the index. I can just decide that the answer is no. We don't have those kinds of mechanisms around cross-data type comparisons. So cross-data type comparisons are sometimes indexable, but there are a number of cases that come up reasonably frequently where they are not indexable. And so if you don't match your data types, you lose. Inlining. We have a mechanism for inlining SQL functions and various other things. If you inline the same time multiple times and end up with many copies of it, that can turn out to be a bad plan. Just doing it once can be more efficient. But the query planner isn't smart enough about that yet. Not in is hard to optimize because it has these really weird semantics about nulls that everybody hates. My personal recommendation is don't use not in with a subquery, because even if you think you know what you're doing, the strange null behavior will eventually bite you if the poor optimization decisions that we make don't bite you first. Use not exists instead. Not in is OK with a list of constants, but with a query, as long as you don't have null as one of those constants. But not in with a subquery, generally you're going to be better off using not exists. The first 3 times you do that, you'll be like, this is really annoying. And then after that, you'll be like, oh, that was easy.
Then you comment here, not exist versus anti-join.
So an anti-join, the question was about not exist versus anti-join. An anti-join is an internal implementation construct, right? So an anti-join is a method of executing a certain query via a join. And there are several different things that you can type that will cause the query planner to decide on an anti-join. So not in and not exists and left join where non-nullable outer column is null are different things that you can write that potentially might be evaluated as an anti-join. But the anti-join is sort of like if we recognize that you're trying to find all the things from here except the ones that match this.
So would you optimize in similar way or in different way, not exist, and like outer join with like whatever is null?
Yeah, so not exists and outer join with whatever is null tend to be optimized similarly. Not in, however, tends to be not as good. And another problem in this area is sometimes the target lists, the final outputs of the query, are computed too early, or there are unnecessary targets that we compute that we don't actually end up needing. This tends to happen with like complex combinations of views and with queries and other stuff where, in theory, if you were careful enough about tracing everything through, you would find, oh, we don't really need that column, or oh, we don't really need that expression. Generally, we're actually pretty good at this. There's only 3 errors in this category. But there are cases where you can do things that are sufficiently strange that you defeat the limited intelligence of the planner in this area. You can't rewrite select max A from foo where B in some list as a max of index scans. This is a simple query rewrite thing, right? If you have a query of that form, you could do an index scan for each possible B value and then just take the maximum of those values. You can actually get that plan by writing this out as max over union all, union all, union all, union all, union all. But if you write it this way, the query planner won't think of using that plan. Joins and aggregates, the query planner cannot rearrange those. If you have an aggregate with a join inside it, it's going to do the join first and then the aggregate. It won't consider postponing some parts of the join until after the aggregation step has been done. We talked about deducing implied inequalities. This is like a.x equals b.x and a.x is less than 1. Logically, that implies that b.x is also less than 1, but we don't know that. The reason why this isn't done is because Tom Lane thinks it would be too expensive and that would hurt planning time too much on too many queries that wouldn't actually benefit. But there certainly are some queries that would benefit, and so there we don't get that benefit. Again, the good news about these kinds of problems, everything in this category is there's some way to rewrite the query in the way that actually does get you the right plan. Because if there weren't, this wouldn't be a conceptual error, a failure to consider two things as equivalent when you really should. It would be an architectural limitation, or we're just bad at that, or it fall in some other category. So these things are actually relatively easy to fix. The big problem here is that there's a lot of potholes. There are 10 other issues that came up once each. Human beings are just so much smarter than computers, and SQL is a very expressive language. There are a lot of ways to write things that are either equivalent to each other or like almost equivalent to each other, but not quite exactly equivalent. And of course, that latter category where it's almost but not quite exactly equivalent, the query planner is never going to be able to pick the right option there because it can't transform between things unless they're 100% logically equivalent. The ones that actually are equivalent, in theory, we can get all of those right, but in practice, the planning time might really go through the roof. So I expect some of these to get improved in future releases as we get smarter and smarter, but some of them are probably never going to go away because everybody in this room can probably think of 10 pathological ways to write a query. It actually might be an interesting exercise to have an obfuscated SQL contest like the obfuscated C contest, because you can definitely do that. Throw in a few unnecessary self-joins. I mean, there's all kinds of things you can do in this category. All right, that's all I got. I can hang around for a couple minutes for questions, and then I think we get to go eat lunch. Any questions? Questions?
I broke that like long question, and if it's long, you tell me it's long. Did you ever consider optimizing OR conditions in terms of OR like union? Because that's what I do manually a lot, and it often seems obvious. And
yeah. So the question is about About or versus unions. Yeah, that's a big one. I think it would be really good if we could be smarter about that, but I haven't had time to work on that code in a couple of years.
Not in the upcoming plans.
Don't think that's in the upcoming plans. Yeah. Was there a question somewhere back there? Yeah.
Seems like a lot of the aggregation stuff really limits the query planner.
Yeah, okay, so the question is about aggregates limiting the query planner. Basically, the way the query planner works right now is when you give it a join, it says, oh, look, I have a bunch of stuff here that I need to figure out how to rearrange. And an aggregate acts like a wall. So, it doesn't know any other strategy other than optimize everything inside the aggregate, then do the aggregate, then maybe optimize more stuff outside the aggregate. So I think the way you would fix that is all the machinery that we have around joins would need to be generalized to handle both joins and aggregates. We have logic for saying, wait, if we're joining A and B and C, what are the legal orders in which to perform those joins, and what are the legal strategies? We would need similar logic for aggregates. I wouldn't be too surprised if we have that 5 years from now, but I'd be very surprised if we have that 1 year from now. So, I think it's probably one of the more important problems in this category because it's possible to work around it by rewriting your query, but it's often annoying to do so. So I would consider that a fairly important problem, and Tom's made noises from time to time about spending some time and effort on it, so you never know when he might just bust out a patch because he tends to do that sort of thing. People who know Tom are laughing. But as far as I know, he's not working on it right now. So we'll have to wait and see whether something happens there. But yeah, it's sort of just a limitation of the structure of the query planner right now. We build these complex data structures for optimizing each join tree, but the grouping planning happens a level above that and really doesn't intermix with the join planning right now. Yeah. Yes. So the question is, are there any plans on how to address the correlated columns problems? I would say there are a lot of plans. Several people have tried to write patches for this. The problem is that as far as I have been able to determine, and with due respect for the hard work that those people have put into developing those patches, they don't really look like they'll actually work very well. So I guess for that reason I'd answer no. Some of the problems that are on this list because we know what to do about it and we just haven't done it yet. But some of the problems on this list, and I think that one is a good example, are on this list because they're really fracking hard. And the correlated columns problem is certainly one that falls in there. And the classic example, right, is if you've got a bunch of addresses in a database and you're querying the state column and the zip code column. State equals something and zip code equals something else. The correlation will either be +1 or -1, depending on the exact pair of values that you put in there. And right now, we always estimate the correlation as 0. So this is a classic example of if this is going on, you really need to be prepared to give very different query plans when the person gives you a state and a zip code that overlap versus when they give you a state and a zip code that are in different parts of the country. If you think you know the answer to this problem, then first of all, you're probably wrong. But secondly, if you are right, I'd really like to talk to you, and I bet a lot of other people would too. I know that there are some other databases out there that have better solutions to this problem than we do. So somebody has figured out how to solve this problem, at least better than we've been able to figure out how to solve it. But those people have not chosen to open source their code, so I don't get to look at it. I think it's a really interesting research problem, and I really do think it's a research problem. If someone were in a PhD program and wanted to do a dissertation on this and came up with something good, I think that would probably make a pretty good PhD topic. It's a hard, hard problem. And so everybody who sits down and says, I know how to solve this, I'm going to start coding something up, is almost certainly just wasting their time, because the problem is a lot harder than that. And so you go all this work, you write all this patch, and then somebody says, you know, you can't even handle the state zip code problem, which is trivial to understand, and everyone in the room can see why it doesn't work with that case. So, you know, what's even the point of this? You're not really addressing, you may be solving some problem that you have in your particular environment, but your solution is obviously not very general. And until somebody can describe in words a solution that is general enough to handle some of those easy to understand cases, I don't think anybody's going to have a lot of confidence in saying, okay, this is part of our core infrastructure. I think we are out of time. I will be happy to hang around for a few minutes afterwards if there are people want to come up and ask me questions individually. But thank you for coming.